So welcome to the second session of the morning. We have Alexander Gamburd, who's going to speak on arithmetic and dynamics on varieties of Markov type.
Thank you very much. I'm delighted to be back in Zurich and give a real talk in front of real audience, and I'd like to thank the organizers for giving me this opportunity. The talk will be centered around the work which is joint with Jean Bourgain and Peter Sarnak, and it started in 2005. I'll say a word about motivation and that history in a moment, but let me start by introducing the Markov equation. Just a moment. Okay. So this is Andrei Andreevich Markov of Markov chains fame. Am I writing big enough? No? Bigger? And this is his thesis, which, this is good? Which, please let me know, and also please ask questions. This is not an official ICM talk, and please ask questions and interrupt me at any time. I think by the end of the talk I'll figure out how this works. So Markov equation, okay, it's important that this one you see. Markov triples are positive integer solution. Markov numbers coordinates of a Markov triple and there is also a notion of a Markov sequence, which is the largest coordinate of a Markov triple counted with multiplicity. Now, this equation appears, so let me denote this variety by x. So this equation appears at the end of Markov's papers. I'm always tempted to say a word about Markov's paper, which is spectacular and fundamental. Malyshev is of the view that the only paper in number theory in 19th century comparable with this one is a paper by Riemann. I wouldn't go so far. Anyway, Markov proved an infinite sequence of theorems. I'll tell you the first two. So there is a result which is generally attributed to Hurwitz, and in fact Hurwitz did give a beautiful and self-contained proof, but it's already in Markov's work. An irrational number admits infinitely many rational approximations P over Q such that alpha minus P over Q is less than 1 over square root of 5 Q squared. This is sharp if alpha is GL to Z equivalent to the golden ratio. No, this is sharp. So for the golden ratio, it is strictly yes. That's the point of it being sharp. So the second result is due to Markov's doctoral advisors, Korkin and Zolotarev. And this is in 1878. So if alpha is not GL2Z equivalent to the golden ratio, then there are infinitely many rational approximations P over Q such that alpha minus P over Q is less than 1 over square root of 8 Q squared. This is sharp. If alpha is GL2Z equivalent to theta 2 equal to 1 plus square root of 2. Now, Markov proves an infinite sequence of these theorems. I'll write down the formula and you'll see what I mean. So alpha minus P over Q is less than mj, j is Markov number, and I'll write them down in a moment, the first few, divided by square root of 9 mj square minus 4, 1 over Q squared. I will not be able to do justice to Markov's work. The paper I would recommend is by Bombieri, called the Markov tree. And the Markov tree is the following object. So there is one solution which is staring you in the face, 1, 1, 1. 1, 1, 2. 1, 2, 5. 1, 5, 13. 2, 5, 29. 1, 13, 34. 5, 13, 194. 2, 29, 169. 5, 29, 433. And let me add one more note to indicate the rapid growth. 29, 433, 37666. And the Markov numbers are read off from this tree as follows. So 1 is what gives you the golden ratio. 2, 5, 13, 29, 34, 89, 169, 194, 233, 433, ... So what am I doing? So there is one solution which I said is staring you in the face, the root solution. And now, if you look at this equation as a quadratic equation in x1, you see that the two solutions are related simply as follows. So x1 plus x1 prime is equal to 3x2, x3. So if you have one solution, you can obtain another solution by applying what is called Vieta involution. And the group generated by these three involutions when you act at the root solution is what gives you the Markov tree. So the Markov tree now I'm going to face the real issue. Anyway, before I face the real issue, so the Markov tree can be viewed as an orbit under the action of gamma of the root solution. That means that the group is nonlinear. The action is nonlinear. So no, I don't have to raise yet. Okay. Sorry. Okay. Okay. So following the publication, the first reference to Markov's work is a paper by Hurwitz in 1907, where he looks at the equation which is now called Markov-Hurwitz equation. And he says, I want to find n tuples of integers such that the sum of their squares is divisible by their product. And at some point he comes to n equals 3 and quotes Markov. But the motivation for looking at this equation is what I just said. And then in 1913, Frobenius wrote a very important paper called Über die Markovschen Zahlen. And he makes a number of observations about these numbers. For example, probably as some of you noticed, they're all sums of two squares. And there are many things happening in this paper. He makes a conjecture, which is still open, asserting that M is equal to MS. It's not going to be important in what follows. It's convenient to assume that it's true. Now, while so Hurwitz's paper was the first paper referencing Markov's paper. The Markov equation itself appears implicitly in the work of Poincaré in 1884, and Vaught 1889, and Fricke 1895, and then Fricke and Klein 1897. And it appears in the form of what is now typically referred to as a Fricke identity. And this is going to be important in what follows. So trace square of A plus trace square of B plus trace square of AB is equal to trace of A, trace of B, trace of AB, plus trace of the commutator plus 2. And in the automorphic form volume, Fricke and Klein devote something like over 50 pages to this equation. And I also look at the shape of the equation, because at some point they comment that this equation appears in the work of von Staudt on the area of spherical triangle. But they never make a connection to the Markov equation, and this is quite striking, because Klein in 1895-96 gave a course on quadratic forms at Göttingen, and there are mimeographed notes of this course, something like 600 pages. I haven't seen reference to Markov's work there. But Klein was also editor of Mathematische Annalen when Markov papers appeared. So either this part of the book was written by Fricke, or Klein really didn't know about Markov's work, or both. In any case, the first time the connection was made was in the work of Kohn in 1955. And I'm going to skip some. So the next question is, how many Markov numbers are there up to t? And let me state this result as an assertion about the number of integral points on Markov surface in a ball of size t. And the result here is that this grows like log t squared. Now this result was first appeared in the thesis of Gamburd. 1976, and he obtains this result by comparing Markov tree with Fari tree. Zagier, and this is published, obtains a better error term by comparing Markov's tree with Euclid tree, and then there are proofs by Mirzakhani. And McShane Reven. And a very beautiful proof is contained in the last paper of Bailey. The best error term here to date, I believe, is given by log t, log t. So what I want to stress is that Markov numbers are sparse. Nth Markov number grows like a to the square root of n. And I don't think I'll have time beyond just stating the result with Magee and Ronan, which is about counting integer points on Hurwitz varieties. And the result here is quite different and surprising. So this is a paper which is joined with Magee and Ronan.
Could you write larger?
I can. Sorry. So if you ask the same question, and this follows earlier work of Baragar. So if I ask this question about Hurwitz varieties, then the exponent here is so beta of 3 is equal to 2. Beta of 4 is numerically given by, well, it's in this interval. And I'm willing to conjecture that for n equals, so in general it's not integral, and I'm willing to conjecture that for n equals 4, say, it is in fact transcendental. I should pay attention to the... Okay, so now so I have to get to 2005 and say, what about our motivation? So I didn't know anything about Markov number. Okay, maybe I should tell you this while I'm erasing the blackboard. I see Manfred is smiling. Oh, actually, I don't have to erase. So, okay, I didn't know anything about Markov number until August of 2005 when I got a letter from Peter Sarnak. He said he has an interesting problem related to my thesis. so so there was this number. There was a school in number theory in China in the summer of 2005, and Peter was organizing it. And during that school, Philippe Michel and Akshay Venkatesh asked him a question which was related to the work they were doing with Anzidler and Lindenstrauss related to Duke's equidistributions theorem. Associated with these irrationalities, there are geodesics, and they wanted fundamental geodesics. So the question they asked, translated into the language that I'm using here, was the following: are there infinitely many square free Markov numbers? So that's what was being asked, and Peter had the insight that this question leads to and demands an affirmative answer to the following one, which is still open. So if we reduce Markov tree mod P, obtain a sequence of graphs, which we call Markov graphs. So the question is, do they form a family of expanders? So this is still open. What we proved and what I will turn to next is that they are connected. So what happened was that, so I should stress again that what makes this problem difficult is the fact that the group is nonlinear one. And so the past 15 years saw very rapid development in the... So this question gave birth to what is now called the fine linear sieve. And in the setting of linear groups, thin linear groups, we by now have a pretty complete understanding of expansion, and consequently we conceive and say that, not only are there infinitely many square free numbers, but there are infinitely many almost primes. And I think it's instructive to very quickly take a look at the example in the linear setting, which is very, in many ways, parallel to the Markov one. So I guess you can call this Descartes equation. So 2x1 square plus x2 square plus x3 square plus x4 squared is equal to x1 plus x2 plus x3 plus x4 squared. So what is this an equation for? There is a result of Apollonius asserting that if you have three mutually tangent circles, there are exactly two other circles tangent to these three. So this is an equation for the curvatures of four mutually tangent circles. Now again, if you look at this equation as a quadratic equation in x1, you see that the two solutions are related simply as follows. So if you have one solution, you can obtain another one by applying Vieta involution. But the transformations, so if I call this transformation A1, and this is an involution which is interchanging the blue and the green circle, so let me call this A2, A3, A4, A1. So if you take the group generated by these four transformations, And you start with an initial configuration, all of whose curvatures are integral. Then, again, this integral, the integral polynomial packings can be viewed as the orbit of A and the lambda. And this is an example of a thin linear group, where, as I said, by now we can prove expansion and consequently sieve. Now, another thing I want to point out is that the number of the elements here are sparse, but not nearly as sparse. So if you count the number of elements in the group up to t, they grow like t to the delta, where this is Hausdorff dimension of the limit set. By the way, I'm willing to conjecture that this number is also transcendental. So if you go one dimension lower, then this sequence will be sparse, but not nearly as sparse as the Markov numbers. So the problem we're dealing with here in the level of difficulty is much simpler than, much harder than the case of thin linear groups, but it is much harder than the case of tori, where the strong approximation assertion essentially amounts to Artin's conjecture. Okay, let's see if I can do it. I think 10 years ago I could do it. I shouldn't have been, okay, I erased the tree. Okay, I shouldn't be distracting myself. Let me just erase this. Sorry?
What is the structure of this Markov group?
So I think it is just a product of, it's a free product of, yes. For the Hurwitz group, it's a little bit more complicated, and I have reference in my. So as a group, it is not. As a group, it is just a free product. But the action is nonlinear. Okay, I think I'm supposed to. Horizontal is better. Okay. Yes, of course it's okay. And maybe this is the last. Okay, where was I? Oh yeah, I said it's simpler than. Yeah, I said it's harder than the case. It's harder than thin linear groups, but it's harder than the case of tori, where the strong approximation amounts to. So okay, so we cannot answer the question that was posed by Michel and Venkatesh. What we can prove as a consequence of proving strong approximation is the following. So what we can prove is almost all Markov numbers are composite. And when you first hear this result, it doesn't sound terribly impressive. Almost all numbers are composite. But even that takes a bit of a proof. That was the second result that Euler proved after proving that there are infinitely many primes. It shows that there are not too many primes. And if you look at the sequences which are sparse, I guess if you look at this sequence, which I guess one can call Hooley numbers, it is not known whether almost all of them are composite. Even assuming a generalized Riemann hypothesis, which allowed Hooley to give a conditional proof of Artin's conjecture, it is not known he had to make an additional hypothesis, which is something like Artin's conjecture for square-free moduli. So so I defined the Markov graphs informally. Let me define them formally. So we have Markov graphs so I have to tell you what the vertices and edges are. So the vertices are given by reducing the variety, Markov variety mod P, and then removing point 0, 0, 0. And this might seem like a cosmetic change that I'm making, but in more general situation, one first has to understand what are the finite orbits over C and remove them before the statement amounting to strong approximation is made. So these are vertices, and then we connect x to R1 of x, R2 of x, R3 of x. And then we have the strong approximation conjecture, which asserts that they are connected. And we have a super strong approximation conjecture asserting that they're highly connected, that is to say, form a family of expanders. And these graphs appeared first in what they were looked at in the thesis of Barragar, which I mentioned. We started looking at them in 2005, but the first time the conjecture was made in print was in the paper of McCullough and Wanderley. I will not be writing all the references because I'm running out, but all the references and details can be found in my report. And this conjecture was made by McCullough and Wanderley in the context of what is called product replacement graphs, which let me very quickly review. So the product replacement graphs are, so there is a product replacement algorithm which is used to very quickly produce a random element in a group. And associated with this algorithm, there are product replacement graphs, so vertices. So G is a finite group. Vertices are given by k tuples of generators. And they are connected by essentially Nielsen transformation. So Rij plus minus is defined as follows. So you take your generators, and then so Gi, Gj plus minus 1, Gk. And similarly, you define Lij plus minus. And people working in group theory looked at them earlier under the name of T-system. And the first result pertaining to connectivity is due to Gilman. I think this is 1977, who proved that if you take SL2P for k greater or equal than 3, they are connected. Now, in 2006, Pak and I, under the same assumption, k greater or equal than 3, proved that they are in fact expanders if SL2P is strongly uniformly expanding. That is to say, expanding with respect to all generators. And this, Breyer and myself proved is true for infinitely many primes of density 1. Now, for k equals 2, you cannot possibly expect connectivity because of the free k identity. And what the conjecture was essentially that commutator is the only obstacle to connectivity. So I'm going to state the results for Markov variety, Markov graphs only. With the exception of theorem 4, which is a recent breakthrough of William Chen, the results hold for more general varieties, and I will comment on this if I have time. So the first result is the following. So, okay. So Markov graphs have a giant connected component which we call a cage. So what is not in the cage is very small. So note that the size of the Markov graphs is roughly p squared. And the second statement here is that every gamma orbit dp satisfies a lower bound of log p to the 1/3. The second result says that the following. So let E be the set of primes for which strong approximation fails. Then this set is also very small. So if you look at the set of exceptions up to T, then this is less than T to the epsilon. Now, the next result is a recent breakthrough of Will Chen, and at the moment, his proof only works for Markov equation. He needs a modular interpretation. The result is the following. So every gamma orbit dp has size divisible by p. The fifth result is the following. So assume that Markov graphs are connected. Well, let me write it this way. Connected. Then they're connected for the moduli z mod p to the kz for all k. And now combining theorems 1, 4, and 5, we obtain the following. So for all sufficiently large p, gamma acts minimally. On the p-adics. And I'm not going to erase another blackboard, but I have a few minutes to say a word about. Sorry? Oh. Okay. So the starting point and inspiration for, so how much time I actually have? 5 minutes, so I can try to say a word about the proof. So the starting point and inspiration for our proof comes from a paper of Goldman, where he proves that the action of gamma on the character variety of one span. Where he proves that the action of gamma on the compact real components of the character variety of the mapping class group of one punctured torus is ergodic, and his proof uses dense twists, and we call them rotations. So you see, if you look at the following transformation, so this is a permutation of the second and third coordinates, and this is R2. So we cannot get very far by just using involutions. If you combine them, you get a transformation which is more interesting. And so this is a rotation. So this preserves conic sections, and if you look at the action of this rotation on the xp intersected with a plane given by xy, you see that x1, x2, x3 is joined to the points x1, d1 to the j, x2, x3, where j is 1, 2, up to t1, where t1 is the order of d1 in SL2P. So if T1 has maximal order, then we cover the full conic section and then connect them by intersection in various planes. And if not, then we want to find in this orbit a point with the order greater than T1. And this leads to the following basic equation. So C is in H1, eta is in H2, H1, H2 are multiplicative subgroups in P star or quadratic extension. Let's see. Now, so if the order is greater than p to the 1/2, then one can apply Weis-bound and obtain a point in the of maximal order. But if the order is less than that, then the genus is too large, and so one cannot apply Weis-bound, and what we use. Well, let me just try. So what we use is Bourgain's let me just try the word. So it's semi-ready theorem for modular hyperbolas. And this is this in turn is deduced from expansion and L2 flattening lemma in SL2 over whichever modulus you need, over prime or Z mod P to the KZ. So I think I'll stop here, but I'll be happy to answer any questions you have. Thank you.
So can you repeat what is on the blackboard, theorem 3? Almost all Markov numbers are composite.
Yes.
And then you said a sentence about the number 2 to the n plus.
So here we do not know. So what I said here is that the Markov numbers grow like a to the square root of n. So this sequence, which grows faster, a little faster, 2 to the n plus b, we do not know if almost all of them are composite. So this is in the book of Hooley, Applications of Sieve Methods. It's in chapter 7. So assuming generalized Riemann hypothesis, Hooley gave a conditional proof of Artin's conjecture. And to prove an analogous result for this sequence, he had to assume something like Artin's conjecture for square-free moduli.
What is Artin conjecture?
That A would be a primitive root for infinitely many primes. I guess this is a small Artin's. This is what. Okay, this is Artin's conjecture, not the Artin's conjecture.
And what is the Artin conjecture needed for solving the question on Hooley number being composite?
Say it again.
You said that you need then a strength, some other form of Artin conjecture to know.
So Artin's conjecture is about A being a primitive root for infinitely many primes. So you need something like a quantitative version of that statement, but not just for primes, but for square-free moduli. And it's a little technical to explicitly state it. But so, by the way, to prove this result, we need strong approximation for square-free moduli. And this could be obtained using semi-ready Trotov for modular hyperbolas. And there is also a proof by Mieri and Pura using an approach very similar to that of Gilman. So Gilman didn't just prove that these graphs are connected. He proves that the action is as a full alternating or symmetric group. And so what Mieri and Pura showed is that where we prove connectivity, the action is in fact as a full alternating group, and then using Goursat's lemma, you deduce that you have connectivity for the square-free moduli. And so that's necessary to obtain the statement here.
Thanks. So, about this theorem on the upper board, counting the points on
Yes.
Vn. So Vn depends on the parameter a. Can you talk about how the constant c and beta n on the right-hand side depend on the choice of a? Are they independent?
So the constant. Okay. So the constant. Sorry. Sorry, just a moment. I want to get it down. And okay. So the constant. So we in fact can look at the following equation, and once you put k here, so first let me just say that the constant depends only on n, and is independent of a and k.
Really?
Yes. Now, for some values of, okay, there is a very subtle question here. There is a very subtle question here, which is subtle already for n equals 3, and that is if you put for general a and k, the first thing you have to understand is whether there is one solution, right? And so if there is one solution, then you have infinitely many solutions. But this issue of just having one solution is very subtle, and this is work of Sarnak and Ghosh and has a principle for Markov varieties. And also for some values of a and k, you would have special solutions where, so for example, when this, for n equals 3, when this degenerates to Cayley surface, then you will have curves which are translated. But in general, the constant depends only on n.
Okay, thank you.
Are there other questions? All right, if not, let's thank the speaker again.